Okay, let's continue working on problems. And the next problem we're going to do is number 22. And number 22 states that a 5 times 10 to the fifth kilogram subway train is brought to a stop from a speed of a half a meter per second in 4/10 of a meter by a large spring at the end of the track. What is the force constant of this spring? And the energy of the spring is equal to the force constant times the x distance that the spring travels squared. That's going to be equal to the kinetic energy that's absorbed by the by the train. And so if we solve this equation for k, the halves cancel out and we end up with mv squared over x squared. And so that's going to be 5 times 10 to the fifth times 0.5 squared divided by 0.4 squared. And if we do the math here, we get 7.81 times 10 to the fifth newtons per meter. So that means that for every meter that this spring is collapsed, it absorbs this much force. Number 23 states a pogo stick has a spring with a force constant of 2.50 times 10 to the fourth newtons per meter, and it can be compressed a total of 12 centimeters, which is 0.12 meters. To what maximum height can a child on this pogo stick, using only the energy of the spring, if the child and the stick have a total mass of 40 kilograms? Well, we have a similar equation, but now we're converting the spring's energy into potential energy. So it's going to be 1/2 kx squared is equal to mgh. And in this case, and we've solved this for h, we have kx squared is equal to 2 times g times m. So this is going to be 2.5 times 10 to the fourth times 1.12 squared divided by 2 times 9.8 times 40. And that's going to give us a height of 0.459 meters, which moves into something called non-conservative forces. A 60 kilogram skier, so the mass is equal to 60 kilograms, has an initial speed of 12 meters per second, and they coast up a 2.5 meter high rise shown in figure 70.4. I'll draw that in just a second. And so this looks like this. You have a flat slot. Here's the skier. They're heading this way, and they go up a rise that has a height of 2.5 meters, and they end up here. Okay. We also know that it wants us to find the final speed at the top given the coefficient of friction is, so mu, and it's k because they're moving, is 0.080. Okay, so we have the kinetic energy of the person that's moving, or their initial kinetic energy, plus the work done to overcome the friction, which is the non-conservative work, is equal to the kinetic energy at the final plus the potential energy gain also at the final. So this change in height. So that 1/2 mv squared v0 squared plus the friction force times the distance the friction force occurred is equal to 1/2 mv squared final plus mgh. This is going to stay the same, 1/2 mv0 squared, and this is going to be, this is acting against them, so it's a minus mu times the mass times g, that's the normal force, times this, the cosine of this angle. And that's going to times the height divided by the sine of the angle, because that's the distance this hypotenuse is the height divided by the sine. And that's going to equal, in other words, this is the calculation of the friction force. This cosine theta corrects the downward to the fact that this is on an angle, theta. And this is the distance this is the friction force here, and this is the distance that friction force has to be applied. And that has to equal 1/2 mvf squared plus mgh. So if we do a bunch of rearranging of all this mess, we end up with Vf is equal to the square root of V0 squared minus 2gh times 1 plus mu times the cosine of theta. And theta here is 35 degrees. I need to write that in. And so Vf is equal to 12 squared minus 2 times 9.8 times 2.5 times 1 plus 0.08 and times the cosine of 35 degrees. And that equals 9.46 meters per second. Actually, unfortunately, it's not cosine. When you do this calculation through here, you end up with something called the cosine over the sine. And the cosine over the sine is equal to an entity called the cotangent. And so this is actually cotangent. And I know that you haven't had enough trigonometry to know what the cotangent is, but it's the cotangent is just equal to 1 over the tangent. And this part you wouldn't know, but if you put numbers in at this point up here, instead of trying to, this is cotangent here, if you put numbers in here, you get the same answer, and which is how I did this problem originally. Let's move on to number 25. Number 25 states the following. By a hill can a car coast up, engine disengaged, if the work done by friction is negligible and its initial speed is 110 kilometers per hour. So we start out with 110 kilometers per hour. That's going to be equal to, I'm not going to go through showing you all the work here, but that is equal to 30.556 meters per second. And I know I didn't do significant figures here, but I did that on purpose. And we know that 1/2 mv squared is equal to mgh in this case. what they're basically saying is that this car rolls until it stops, and all of its kinetic energy is converted into potential energy, how far up the hill will it roll? Now, the mass of the car you don't need to know because it's on both sides of this equation. So you end up with V0 squared over 2 times G is equal to H. So 30.556 divided by squared times 2 times 9.8. And if you do the math here, you get 48 meters. Now the second part of this question, if in actuality a 750 kilogram car with an initial speed same is observed to coast up a hill 22 meters above its starting port, how much thermal energy was generated by friction? So if they give you the height, now all of this kinetic energy is not being converted to potential energy, but it's being converted into a combination of potential energy plus the heat. We can note this any particular way you want to. The work due to heat. And so the change here is that you know that you have 1/2 times 750 times 30.556 squared is equal to 750 times 9.8 times 22 plus this heat factor. And if you do this calculation, the work of heat, if you solve this for W, you get 1.9 times 10 to the 5th joules is lost due to heat and friction. Now the third question says, what is the average force of friction if the hill has a slope of of 25 degrees? So what is the average force of friction? So we know it's going up a hill. This is 25. This is the length, or D. I've been using D a lot. And so the height is going to equal L sine 25 degrees. So L is equal to H over the sine of 25 degrees. If we put the numbers in, that's 50.5 meters in length. And work is equal to force times the length, so that 1.9 times 10 to the 5th, we got from here, is going to equal the force times 50.5. So F is going to equal 380 newtons to two significant figures. It's 376, but to two significant figures, it's 380. This is actually 505 meters, not 500. This dot is wrong. I'm sorry, this is 2.5 degrees here, not 25 degrees. And so this is the sine of 2.5 degrees and the sine of 2.5 degrees. And that's why that's 505, not 50.5. Let's do one more problem before we switch videos. We'll do number 27. Problem number 27. Using energy considerations and assuming negligible air resistance, show that a rock thrown from a bridge 20 meters above the water at an initial speed of 15 meters per second strikes the water at a speed of 24.8 meters per second, independent of the direction shown. Now the key here is using the energy considerations. So you have 1/2 mv squared initial plus the change in potential energy is going to equal 1/2 mv squared final for the conservation of energy. And if we delete the m's, because they're in all these places, we get v0 squared plus 2gh is equal to vf squared. So vf is equal to the square root of v0 squared plus 2gh. So that's going to equal square root of 15 squared plus 2 times 9.8, and the height here is 20 meters, and you get 24.8 meters per second, which is what they said in the original problem.